Welcome to the second part of the afternoon session. We have two more talks, and we're going to start with volume B.
No? Okay. Okay.
Who will help us explore inflationary magnetogenesis.
Okay, thank you. First of all, I would like to thank the organizer to having me here to report the work of our groups in recent years. So the plan of my talks will go like this. First of all, I will briefly describe the background of the work, and then I'll employ the so-called spinodal instability mechanism to create primordial magnetic field, that is PMF, in a very simple chaotic inflation model. And after that, I'll generalize our scenario to include the dilaton electromagnetic field. The reason I'll explain in my talk. And then after that, I'll turn our attention to investigate the issue of back reaction in the production of PMF. And finally, I'll show you the preliminary result of our current work. Okay. Now, basically, we know that there is a observed cluster and galactic magnetic fields of about a few Gauss, which might be resulted from the amplification of a C field about 10 to the 23 Gauss via the so-called galactic dynamo effect. But through the most of the history, the universe has been a good conductor which preserves the magnetic flux, so that the ratio of rho b, the energy density of the magnetic field, versus the energy density of the photon remains a constant. Okay, so namely, rho b will be about 10 to the minus 34 times that of the energy, that of the photon. So, and this number will serve as the standard that to identify whether we will have a successful model to create PMF later. And the C field may be generated inside or outside the Hubble horizon. And in this talk, I'll focus on the part that the PMF was generated outside the Hubble horizon. And in that, I mean, I'll basically use the principle of constructing structure by cosmic inflation to reach the goal. Namely, when the magnetic C field would basically arise during the inflation, and at some point it will leave the Hubble horizon, and the subsequent evolution has to wait until after the inflation, the horizon size catch up the superhorizon size of the magnetic field. So that we argue that the magnetic field is actually follow the evolution track like this. Okay, and to fulfill the creation, the requirement of the creation of magnetic field, we have to overcome a problem that, because we know basically the standard Maxwellian field is invariant under the conformal transformation. So So the evolution equation of abelian gauge fields are basically the same in flat space-time and in a conformally flat Friedmann-Robertson-Walker space-time. So to create, to create a magnetic field, a PMF, we have to find a way to break such a conformal invariance. So there are several proposals in the literature, such as in the paper by Turner and Widrow in 1988, they proposed these are the conformal breaking term. And 1992, in the paper by Ratra, there are the conformal breaking term like this, and also in the papers by Carroll et al., they propose a conformal breaking term like this. Okay, what we would do in the following is just generalize their proposal to extend the possible generation of the primordial magnetic field during inflation. So we consider actually in a spatially flat universe that there is a pseudo-scalar field phi characterized by the action here, and this is the normal Maxwellian field, and along with the 5-photon coupling terms, so the action would look like this, and this is FF tilde here. Okay, so the comoving magnetic field can be expressed in terms of the coordinates, comoving coordinates, so that this could be is actually the equation of motion for the B field. Okay, and we can using the follow the usual drill. This magnetic field can be recasted by its corresponding vector field, which contains a mole function V here, and so we can derive the mole equation such that the equation of motion for the mole function looks like here. Okay, here the Q here is actually the dimensionless comoving wave vector in terms of H, the Hubble parameter at the time. Okay, now we can see that basically this equation can be solved so that the mole, the mole of the growing mole, the solution will be proportional to the exponential omega times eta, in which the omega here is somehow determined by the wave vector and also the speed of the scalar field. Okay, theta here is basically the dimensionless phi, which I have rescaled it in terms of H. Okay, so and we also this is basically the so-called spinado instability, and we would actually employ this method and use the most simple inflation model to realize it. Okay, and we can also calculate the energy density of electromagnetic field by this, which include the energy density of the electric field and the energy density of the magnetic field here. Okay. Now, so we consider if you vary in the action, you would naturally obtain the equation of motion for the field for the infotone phi. But we actually ignore any feedback or back reaction from the Maxwellian field and the photon 5-photon coupling. So the background evolution equation for the phi field is usual, okay, and we identify the inflation duration when the infotone field enter into the horizontal trajectory, which simplify the Thorough regime, okay. And basically, in this phase diagram, you can see different initial condition will give out different solutions, but all of them will actually enter into the attractor region, which signify, as I mentioned, which signify the Thorough stage of the inflation, and we put our initial condition around here, so and fix the total duration to be 60. Okay. So the solution here present here is one of the successful solution we have create a primordial magnetic field, and which has a peak at Q around 60. However, the problem is this: the coupling constant here is tremendously huge. Okay, so that basically is not we cannot trust such a generation. So our calculation shows that basically if we count the duration of inflation only on the Thorough, only from the Thorough, then the creation of the primordial magnetic field is not enough. Okay, basically this is the ratio R 10 to the minus 34 here, and this is the coupling constant C here. From this diagram, you can see that this R versus C diagram suggests that the magnetogenesis induced by the spinato's instability in the Thorough region is not sufficient enough, and so our strategy to bring down the coupling constant is basically to involve to include a faster stage for our calculation. Okay, so the faster stage is basically the stage before the infotone enter into the Thorough regime. So if we include the faster stage, that may be able to create more PMF. The reason is that basically we have seen this. Okay, the angle of the frequency here is determined not only by the comoving vector, but also by the field velocity, the velocity of the field. Okay, so if we include such a faster stage, we successfully bring down the equation, the coupling constant from something like over 20,000 to in this case C equals 12.7. Okay, and so that would be great. However, we encounter another problem. In this diagram, we demonstrate that the ratio of rho B versus rho phi. And you can see that for most stage of the inflation, the energy density of magnetic field is actually way over the energy density of the phi field. That is, we have no way to create a large enough magnetic field, even if we have transferred all of the influence energy into the magnetic field. Okay, so apparently this is not good for us. Okay, so in order to improve or in order to correct this, to avoid the energy constraint problem, we actually include, in addition to the X-ion case, we include a dilaton case in our action. Okay, so the infiltrant field and the thermal background evolution is usual. Once again, we have ignored all the possible back reaction here. And on the other hand, the mole function equation for the electromagnetic field will look like this. Okay. Now, and the EM field, the energy density of EM field and the energy density of the B field can also be calculated in this way. And in the case for dilaton electromagnetic field, we have J of tau here vanished, and I as a function of tau. Okay. In a strong coupling case, because the coupling constant is proportional, is inversely proportional to I. So when I of tau is less than 1, which signifies the strong coupling case, we should have a strong enough primordial magnetic field. Although under a situation, the solution may not be trusted because the strong coupling mechanism may not be stable. Okay. On the other hand, we can look for weak coupling case in which I of tau be greater than 1. But under the circumstances, no sizable PMF can be produced. Okay, as before. And on the other hand, this is the X-ion EMF case in which I equals 1, and J of tau equals alpha phi over F. In this case, well, we actually recover the previous solutions. Okay, but the spinodal instability seems to be not effective, as I have shown you before. So, so we start to look at the solution of the mole function by using I of tau and J of tau in these two forms, in which N, C, and P are constants. Okay, and so we do the following calculation using different models. For example, in this model, N equals 1, P equals 0.064, and after the magnetic field, primordial magnetic field goes beyond the threshold, we bring down the N to minus 3.1, and C from 0.5 bring it down to 0 in order to avoid the overproduction of the primordial magnetic field. Okay. In our models, we can actually produce such a primordial magnetic field in this way, in which P equals 0.1 and C equals 1, and N from 0.1 to minus 4.7. And you can see that the diagram in the left-hand side is actually the energy constraint for the primordial magnetic field and versus all of the background energy density. So this is a successful result. We can also check up in the weak weak coupling case. We cannot bring up the enough power on the PMF. Okay, so I should give a brief summary on this study. Say that it is manageable to produce a strong enough primordial magnetic field at the end of inflation in a generalized scenario of axion dynamics with a time-dependent coupling constant like this, provided that J of A delays the growth of the magnetic field to a later stage of inflation. Okay, you can see that in our study, the form of the coupling functions is quite somehow artificial, but for some reason, if nature allows, we can actually generate enough primordial magnetic field in this way. Okay. However, the more interesting thing is that the effect of back reaction due to the rapid production of high K moles seems inevitable. So in the following, we actually take into account such a back action in the mole equation to study how the production of high K moles can be self-regulated by the back reaction. So, so now we retrieve the back action term into the evolution of the background. And you can see that this is the back action term. And also the energy density of the EM field has entered into the Hubble parameters here. Okay, so we can also derive the mole equation, and this is similar as before, but there is a variable here, C equals alpha phi dot over 2FH, and we can once again calculate the energy density in EM field, and also the back reaction can be determined in this way. Okay, so now we can compare our result with the back reaction to the results that we obtain without back reaction, and this is the diagram showing that this is actually the phase diagram for the phi field for the infoturn. The dashed line here, the red dashed line here, represent the solution without back reaction, and the blue solid line here is actually the solution solved with the back reaction. Okay, so you can see that basically the trajectory of the phi field start to deviate from the trajectory without back reaction in this way. Okay, and also this is the phi versus n represent the duration, and this is h versus n, and you can see that also the back reaction actually prevail when the inflation in the later stage of the inflation. Okay. Okay, and the mole equation, the equation motion for the mole function actually change a lot, oscillate a lot in the late stage of the inflation, and so we can also calculate the curvature perturbation accordingly, and this is the diagram that we calculate the curvature perturbation for different models, different alpha. And this dash line, this dot line here, black dot line here is actually the non-detection of primordial black hole bound. Okay, so and another thing is that we have to check the energy constraint. And in this diagram, in different models, we have checked the energy constraint issue, and you can see that all of them are actually the rho EM over rho total is actually less than 1. So when we include the back reaction, the model naturally avoids the energy constraint problem. Okay, so there are actually 3 implications for this situation. First of all, we have a realization of Wong inflation. Okay, if we calculate the temperature of the universe at the end of the inflation, you can see that the temperature represent in this way. Okay, depends on the alpha, and so different value of alpha will give you the different temperature evolution here, and all of them show that the background temperature will actually rise if the back reaction is large enough. Okay, so that the large back reaction will heat up the early universe without involving a post-inflationary reheating stage. This type of model is called the Wong inflation. So when we so that means if we have a large enough back reaction, we don't necessarily have to reheat the universe by some unknown reheating mechanism. Okay, and the second implication is actually that we can produce primordial black hole with high stellar mass. Okay, this is another work that we have done previously. This is the power spectrum of the curvature perturbation, and here again, this is the upper bound of non-detection of primordial black hole. The reason that we did this is that because, as you know, in the LIGO experiments, they detect a lot of gravitational wave event from the binary black hole merge, right? But the source of the merge, the binary black hole, usually have mass much larger than say 15 solar mass, and we know that in majority evidence of the astronomical stellar black hole, they have the mass mostly under 15 solar mass. Okay, so we feel that we need a way to explain why the LIGO experiment has come up with so many events with the black hole having their mass greater than say 30 solar mass. Okay, so this is what we have done for that. Okay, and the third implication is actually our goal here, the primordial magnetic field generations. We consider once again, the action including the dilaton EM field such that we have the coupling term like this. Okay, so the equation of motion for the mole equation can be written in this way. Okay, and in our study here, we take the form of the coupling function as exponential b phi square over the Planck mass square. And in this case, for b less than 0, that signifies the strong coupling case. And for b greater than 0, that signifies the weak coupling case. Okay, and we employ the Higgs potential to calculate to apply the Higgs potential in this case to study the Higgs inflation. Okay, and with the back reaction, okay, the background equation with the back reaction here, in which the back reaction, the back action can be can be determined in this way. Okay, now so we go ahead to basically solve the equations, and we find that on the left-hand side, these solutions are solutions without back reaction, and on the right-hand side, these solutions are our solution with back reaction, our calculation with back reaction. Okay, and you can see that here, without back reaction, that goes the usual way, but with back reaction, there is a significant increase of magnetic field power until say n equals 60 here. Okay, and also to calculate the differential spectrum versus the Coulomb vector, we cannot see any peak in the PMF production here, but we do see a peak when we involve the back reaction situation. Okay, so with back reaction, a strong enough PMF at a proper scale can be achieved without violating the energy constraint. Okay, so it's time for me to summarize. We basically, in our study, contrary to the conventional wisdom, it seems that possible to generate a large enough PMF through the coupling of the EM field to the infoton, provided that a fast roll stage is involved. Unfortunately, due to the energy constraint, this scenario may not work. Okay, although it seems rather contrived, the dilaton axion magnetogenesis works well, provided that if we have a time-dependent coupling function, which would postpone the growth of the magnetic field to a later stage of inflation. But most importantly, in our preliminary results showed before, the inflationary magnetogenesis looks very promising when the back reaction is taken into account. And we are working to refine our numerical scheme to increase the ratio R to fit the new observational constraint reported in the literature. Okay, that will be all. Thank you for your attention.
For the effective the axial coupling case, you don't need a reheating process. When you show the plot for the phi, it doesn't, when you include the back reaction, it doesn't seem to have the oscillation part. For the phi.
For the phi,
Mm.
this,
Earlier, the effective action. Yeah, this one. So leg one is without back reaction. So now you have the reheating
Yeah.
process. But
Yeah.
here you don't need a reheating.
well, depends on how large the variation you,
So if
you consider.
go further, then you can have a,
yeah.
because I worry about the structure forming. Because in this scenario,
Mm-hmm.
in order to have the reheating, you don't need to actually have the reheating from the phi.
Uh-huh.
Just the temperature, the action just can give enough the reheating temperature.
Oh,
But at the end of the day, we need the reheating from the scalar field in order to have the structure formation. So
well, basically, you can see that, you can see that when we include the back reaction, the duration has been sustained for a longer time. Okay, so that basically tell you the infotone has not reached into the global minimum. Okay, so we basically avoid that post-inflationary reheating stage with big back reaction.
Any other questions?
In some slide you said realize some warm influence.
Mm-hmm.
So then my question is then there is a thermal background, right, induced by the infinite production.
Yeah.
Then my question is, if there is such a thermal plasma, then photon also will get thermal mass.
Photon would be
Thermal mass.
thermal mass.
Yeah. So that will, my guess is that will also prevent some exponential production of the gauge field. So tachyonic condition, I mean, when you consider
Oh, tachyon.
condition, so there is not only a Q square, but plus some thermal mass square.
No, we didn't consider that.
So, I mean, so yeah, my question is, anyway, there could be such a kind of effect.
I don't know. Sorry.
Can you show the action,
Mm-hmm.
initial action?
The action. This one?
Suppose that there is no scalar field, then there is simply magnetic flow with thread. So,
This one?
suppose that there is
Yeah.
no scalar field, then
There's no way. Yeah.
you have only F mu mu.
Yeah. So this is the conformal breaking term.
Yeah. So
Yeah.
for the most simple case with only F mu mu,
Mm-hmm.
for that, what the evolution is going to be this F mu mu.
Oh, for the most simple case,
Yeah, most F mu mu only with the thread.
this one.
Yeah. Maybe
There's no way that you can create.
yeah.
Yeah.
Regardless of this creation,
Mhm.
probably people have worked on it. This the evolution of F.
Oh, okay. I don't know.
So even in the presence of this scalar field,
Mhm.
there was some initial electromagnetic field,
Mm-hmm.
right?
Yeah. Yeah.
Yeah.
There was some initially
Yeah, yeah.
electromagnetic field,
Mm-hmm.
but during the evolution, the energy from the scalar field
Will
went into the
convert into the
electromagnetic field, but that not continue, but stop at some point.
Uh,
Stabilized?
you mean this with this term?
Right. The density of electromagnetic field
Uh-huh.
will be stabilized.
Yeah, if we include the back reaction.
Uh-huh.
But if we, yeah, okay, this one is here. Yeah, okay. You can see that if we this is a result that include the back reaction, and this is the ratio of EM field versus the total energy density. So so that's what I meant. If we include the back reaction, we can avoid such a energy constraint problem because in all of situations that we calculate, this is probably 1. And the EM field that create through the coupling will not exceed the background energy density. So that's good. But if you don't include the back reaction term, that will go overflow. Okay. So back reaction is good.
It's necessary.
Yeah, and necessary. Yeah.
Any more questions?
Okay.
Thank you again.
Thank you. It's your turn.
Okay, our next speaker is So-Chun Lee, who will tell us about the reconstruction of F of G gravity models.
Okay, yeah, thanks for the perfect pronunciation for my name. And also thanks for the organizer for nice invitation. So today I'm going to talk about the reconstruct of the Gauss-Bonnet, generalized Gauss-Bonnet gravity. Because of the late time evolution, it seemed to be, as we already heard about the supernovae observation from Mr. Koo today, the current observation seems to be universe is accelerating expansion. And there's two major ways to explain the current accelerating universe by including the dark energy, or we need introducing the modified gravity in addition to the Hilbert-Einstein action. So this work is actually the collaboration with Gansak here. And the way we wanted to do is not only introduce just F of G, one of the F of G model, we try to reconstruct some observational values as a background and the perturbation equation. And we compare that one to the general F of G model and then solve the numerical calculation based on the observed quantity and matching some numerically calculated value as some analytic function to reconstruct the generalized F of G, the Gauss-Bonnet theory. So let me go through. So main reason we think about the generalized Hilbert-Einstein action currently is after people successfully reproduce the CMB and large-scale structure based on the Big Bang plus the inflation, everything seemed to be perfect except we needed some extra budget because before the 1998, before supernova data, almost every observation say that the dark matter plus the baryon, we need about 30%. And universe seemed to be flat. So, but the supernovae, only the supernovae say the current expansion was decelerated instead of the accelerated. So if you input the 70% of the dark energy, current expansion should be accelerating, but the supernovae was against that up to the 97. And from the 1998, they have the late time, because the current accelerating universe is started only after about the 10 billion years old. So before that area, most of the supernovae data from the earlier supernovae data, so they still is in phase of the deceleration. But after then, they have discovered the accelerating expansion directly, and then people worry about the dark energy effect. And even further, because usually supernovae data, still there's some argue about how we make as we saw in the previous session, making the light curve of the supernova type 1a is still arguable, but most of the supernovae data prefer the so-called as a phantom dark energy, means the pressure is, when you rewrite the pressure versus the energy density, a cosmological constant, usually the pressure is the same as energy density with the minus sign. But what data prefer is usually that the equation of state should be smaller than -1. And that means if you solve the energy conservation, Bianchi identity equation, that means if the equation of state is smaller than -1, then A is, as time goes, the size of the universe is increased, then you have the increase of the energy density as the universe increase. So it's against the energy conservation. You should have some energy creation in order to explain the phenomena. So if some people believe that maybe supernovae data is not completely well controlled, there should be some systematic, as you see in the light curve fitting, then you don't need to worry about this one. But if you're really serious about accepting the phantom phenomena in the supernovae data, then particle physics-based dark energy model is not easy to understand this effect, except some negative kinetic energy term, so-called phantom dark energy. Then you have a cost problem in the minus kinetic term. So people started to think about the modified gravity instead of just Einstein-Hilbert action in the action. You can put some general function of the R, so-called f of R, or some modified Gauss-Bonnet term to have the additional effect as the effective dark energy from the gravity side, not from the particle physics side. In that case, you don't need to worry about the phantom cost problem. So as you can see, this is based on this paper, and the best fit is slightly smaller than -1, but as a 1 sigma level is still acceptable. You see? So as a 1 sigma level, 2 sigma level, -1 is still included. So if you don't worry too much about this kind of effect, then you can just working on the dark energy or modified gravity. But if you seriously believe that the equation of state is smaller than -1, modified gravity is more natural than dark energy. And also, this is a dark energy survey, including the supernovae and the photometric BAO, baryon acoustic oscillation, and or the rho Z supernovae. And rho Z supernovae always prefer the phantom region. But it depends on what kind of data you use, CMB as a Planck or WMAP, or even the supernovae, which kind of supernovae you use. This kind of contour can be changed still. As you can see, it's still marginally, even the equation of state up to the -0.5 is still acceptable. So the cosmology is still not well constrained, not like the particle physics. So main motivation is try to check the modified gravity based on the phenomena. And f of r is actually well studied. And then there's also some Gauss-Bonnet f of g gravity was studied, but not much work was haven't been done compared to f of r. And also some people try to even extend the Gauss-Bonnet to have the more higher derivative terms and so-called Hordensky and etc. So we work on this project as an intermediate to go for the Hordensky. So main strategy is like this. So we don't want to assume any special form of the f of g. Usual way is people put some analytic form of the f of g and try to matching the coefficient of the model based on the data. But we don't want to do that. So what we want to do is we want to write down all the equation based on the observed quantity, which is from the background we can constrain the equation of state. And from the perturbation, large scale structure, like the Sloan digital sky survey, we can obtain the so-called growth rate index. I will show you what that means is. And then from this quantity, we can rewrite down all the necessary equation. And we can compare that one as an equation obtained from the general f of g. And then if we can obtain these values, we can solve this equation. This will be the higher order derivative, so f of g usually became a third order derivative. And then we can solve the numerical equation of this one and try to find the analytic solution of that, which can show the reconstructed observation from the numerical calculation. So this is a general just Hilbert-Einstein action plus the generalized f of g. You can think about some general power of the Gauss-Bonnet term. If you have just one, then yeah, there's no change in the Einstein equation. And matter, we just including the baryon and the dark matter. So you can just write down all the necessary equation. This is just straightforward. And as you can see, compared to the usual Einstein equation, you can have the effective matter term in here, dark energy term. Energy density of the dark energy can be rewrite down by using the f term. Small f is f of g, and capital F is just a derivative of the small f with respect to the Gauss-Bonnet. And this is accelerated term, so you can have the effective dark energy term in terms of the just f of g. So as long as your function can reproduce the dark energy effect, this one is dominated at the late time, and this one gives us the close to -1 over the equation of state. You can reproduce the phenomena. That's the strategy. One thing is, compared to the f of r, FG model usually have the term like this. And the prime in here is with respect to the number of e-folding, n log a. So the exponential a, sorry. If you check the h prime over h, this one can be smaller than -1.5. Means in our numerical calculation, so h prime over h can be varied from -1.5 to the -2. So the bigger than -2. So f of r case, we don't need to worry about any form of the f of r. But f of g, this one can be close to the 0. That means in our numerical calculation, if this term is included in the denominator, there should be some singularity. So general f of g model cannot be accepted. We should add some number in here, which should be bigger than 0.5, in order to avoid the singularity problem, which is not considered in the literatures. But we should have some additional term. And
that singularity is a real singularity or just
in the calculation, so because when you rewrite down every quantity, like for example, this one will became an effective equation of state. So when you need to combine this one divided by this one. And in here, this term have some terms like this in the denominator. So numerically, if you have that term in the zero crossing, singularity happens. So it's nonsense. So
physically, then there's no divergence, or
physically, as long as you have the zero term in here, it's okay. But when you, the numerical calculation, so what's the physical motivation of the singularity is just numerical, so not the physical. And in order to solve all the equation, it's better to use because we're working on the numerical calculation, so all the quantity in here is all dimension 4. It's a mass square. So it's better to rewrite down everything with the dimensionless quantity. Easiest way is just to convert everything is dividing by the h0 square, as you can see in here. Then every quantity in here, this is 1 over t square, mass square. So if you divide by the h square, the present value of the Hubble parameter, then you can make everything as the dimensionless quantity, which is suitable for working with the numerical calculation. Also, it's better to using the number of e-folding, convert all the equation based on the number of e-folding differentiation. This is the perturbation of delta m is a delta rho over rho, matter fluctuation. And as you can see, in the general GR case, this is 1. And in general modified gravity, which modified gravity you want to handle with, as long as you're working on the sub-horizon scale, means the horizon is inside, then this unique feature of the modified gravity is this is different from 1. And usually it has the smaller, slightly changing from the 1, which shows us the different behavior in the large scale structure. So as you can see, we can write down those terms as a function of f. So you don't need to worry about all the details, and it's just a straightforward calculation. And this is a strategy. So from the observation, what you obtain is for the background evolution, this is velocity over the background, this is acceleration over the background, and this is a matter fluctuation as a function of log A, number of e-folding. Then in cosmology, usually even though this is not exact, this behavior is well matched as long as you're working in the lambda CDM behavior. So as long as the lambda CDM or de Sitter case, this is just number 1 as you expected. The delta m grow as a scale factor in the matter domination epoch. Then omega m is 1, so this is always 1. A divided by A differentiated by A, so this is always 1. But this feeding formula is well matched with the numerical calculation, even in the lambda CDM. So observational people, what do is they try to find this value in observation. So far, in the lambda CDM expectation, this value is about 0.58. DGP, large scale, the XR dimension, this value is about 0.63. The F over R, this is about 0.45. So, but error bar still in the large scale structure is about 20%. So almost every model can pass this value. So we cannot distinguish which the modified gravity is a better fit with the data. But we hope in the future the error bar in the large scale structure can pin down the 5%. Then maybe this value can be pinned down to distinguish which modified gravity was better than the other. So this is the observational quantity, and this is from the f of g. So we can compare these two values. From the observation, we obtain this one, and we can compare that one with the f of g. So this is a third order differential equation. So we need three initial conditions to solve this equation numerically. But from the equation itself, we only have two. We can obtain only two initial conditions. So one initial condition is we should assume or we should derive. And one way is so in order to solve this mass equation, we need three initial conditions, but we have only two. But one constraint can be obtained from the stability of the f of g, which is the second derivative of the f should be positive in order to satisfy the stability condition of the method fluctuation and also the model itself. So even though we have two initial conditions, we have the constraint on the third initial condition to satisfy the second derivative of f is positive. So we use that. And as an observational constraint, we use the CMB Planck and the Sponnevi and the Hubble expansion and BAO. And this one is most stringent. And as you can see, actually what you obtain is different from the Planck. Planck usually this value is 0.3. Here we obtain the 0.28. Is still okay. And gamma 0 is similar to the lambda CDM, about 0.58. So let me just skip it. This is because our result is similar to the WMAP instead of Planck. The reason is Planck data. Now actually, this is the WMAP data up to the third peak. Planck data, they reach to the about 2000. WMAP is up to the 800. So usually people claim that Planck have the better resolution compared to the WMAP, so which is more reliable, but it's not the case because if you go to the smaller scale means there will be the lensing effect. So we don't have any good, so far we don't have any good theory to analyze this data in the large L. So the deviation, the difference between the WMAP and Planck is still arguable. But usually the referee prefer the Planck because it's nearer than the WMAP. So this is a Planck. Actually, this is a WMAP 7-year data. And as you can see, Hubble and the dark matter is actually consistent with all the other observations at that time. From the WMAP 9 up to the WMAP 7 was read by, before the WMAP to WMAP 3 is read by Spergel. And from the WMAP 5 is read by the Komatsu up to the 7. From 9, analysis is go to the European group, which is actually the same group as a Planck. So as you can see, even though they use the same data, WMAP 9 data is started to have the slightly smaller H0. And the omega C is started to increase. And when the PR, the Planck release 1 at the 2013, their only selling point is because people complain about what's the difference with the WMAP and Planck. Because they spend more money, but there's not much difference. The main target was actually we want to measure the B mode or E mode, but Planck doesn't have a sensitivity to measure the B mode. And then their selling point at that time is they have less dark energy. Instead of 73, now we only need 68. And in the real data analysis, what we do is we should have the constraint the omega m h square. So if omega m is increased, now your h has no choice but that should be decreased. So even that issue was, the people already know H0 was much smaller than other observation. But it wasn't issued at the 2013. And then, as you can notice, it started to have the issues from the so 2017 and 18. So you don't need to too much worry about the tension. It may not be the tension at all. We need another observation. So this is a calculated value. So it may not be the real tension. Anyway, so even though we have as long as you including the large scale structure information, you start to go back to the WMAP. It's more consistent with than the Planck. In any case, what we did is we solved the numerical calculation and tried to compare that with some fitting formula. Even though this one has some strange form, I don't know what it really means, but because after we obtain the numerical, this is the blue one, blue dashed line is a numerical calculation, and then red one is analytic fitting formula. But even though it seems to be matched, the power in here is M1 and M1 and N1 is about 0.65 or 10 to the minus 2. And do we have any theory like that power in any gravity theory? It may not. So it's just a phenomenological fitting form. So this is a matching is the observational quantity with the lambda CDM, means equation of state fixed as -1. This is when we allow the equation of state is changed. And not changed, different from the -1. Then as you can see, the numerical calculation and analytic form, we can perfectly match it. But again, the power in the M1 and N1 is still about -2, and -2 we may ignore. But what's the meaning of the 0.84 in Gauss-Bonnet term is not, we don't have any meaning for that. And if we assume that the Planck-like the data, even though we don't have that value, but we just accept the Planck one, then we can have the two analytic form which well match the observation quantity. Again, the power in here is about 0.84 and 0.81. So even though we can have some analytic form like this, that's what usually the theoretical cosmologists do. We don't know what's the physical origin of this function, but we just matching with the observation and say this is well produced observation. So yeah, that's it. Thank you.
Questions?
In the previous slide, for these model parameters M1 and N1, probably prefer integer numbers.
Right, yeah, that's what I expect.
So the possibility is you have more powers
On,
polynomials.
oh,
So
you're adding more.
parameters and keep the integer power and see whether the observational data can be fit by
I see.
adjusting the coefficients of the polynomials.
Like a C1,
I
G1.
have more coefficients in front of each polynomial.
I see.
So have you tried that possibility instead of this?
So you suggest adding more polynomial powers
Right.
and then try the feeding. Yeah, I didn't try, but yeah, maybe that's one way. Yeah. Thank you. Thanks for suggestion. In that case, maybe we can try the exponential first, because yeah, that may be the yeah, because yeah, coefficient will be different, so it may be difficult, but yeah.
So just we can have four coefficients, A1, A2, B1, B2 with fixed.
Data. So data point in the numerical solution is yeah, maybe I need to increase that because if you have more and more the terms, then of course you may have a better feeding, but may not be. Yeah, I don't know. Yeah, I will try. Thank you. But yeah, this is having the integer power is yeah, better.
Really strange.
This is just a phenomenological fitting, and usually f of r is the same. Most viable f of r model also have some power, but the integer is some strange number, and we cannot find any theoretical origin of that. But people don't care. But yeah, maybe better to extend and check. Yeah, thank you. Thanks for the suggestion.
For the fitting formula for small integer number, I believe I can think some log function, log g, because if I consider some a to d, some epsilon factor, then that can be expanded in terms of log a. So then give the epsilon log a. But I think that, but I mean, but that is based on the assumption that g tilde a is positive definitely. So, but in realistic case, so g also crosses zero, so it can be negative. So then I think, so I'm really curious about what would be in real case. So,
when you allowed that crossing.
so then I think that form could be quite useful.
So even though I didn't explain detail, here as you can see the GA previously we used the f of g means the g just the Gauss-Bonnet term of the general power, but here GA means the Gauss-Bonnet plus the A term which is protecting the crossing minus crossing the zero. So this term is including the G plus that A term. So, but the problem is, even though that suggestion is seem to be interesting, but in that case we cannot do any numerical work because the sum quantity is evolved in the denominator. So the code cannot run anymore. So, but maybe I can think about how to avoid that, and maybe it's worth to think about that probably.
That A is constant?
The A is, in order to protect the denominator, is not zero. So as you can see, at the very beginning, here, G is this term. And the H prime over H can be smaller as like the minus 1.5. So that means it started from the positive and it can go to the zero and then became negative. And if that term is included in the denominator, then we cannot run the code in the simulation, the numerical calculation. So GA means in order to avoid that kind of the crossing zero, we add the which is bigger than 0.5, some constant term put in by hand.
Now what's the difference from just adding the cosmic constant?
No. So that this one means G is the original definition is just this one in flat universe, but this term is in the gravity part, not on the dark energy part. So because of avoid the numerical singularity problem, we just modify general G cannot be the function. We should adding some additional term, H fourth term in the f of g. That's our argue. If you just using the f of g, numerically it can cross the zero. So we should add in the H fourth term with some constant. So it's not really the G, but G plus H4. That's what he added. So instead of original Gauss-Bonnet, we should adding some H4 with some coefficient to avoid the singularity problem. Also physical origin, no. Just in order to avoid that the numerical calculation problem. But we thought, because so far people not considering that kind of problem in general f of g, not general f of g cannot be done that way. So we thought it's necessary to consider some generalized f of g instead of original f of g. Okay? Yeah, thank you.
Okay.
So, out of time.
And
Okay, thank you.